Hello, everybody. Today we'll be presenting hardware-based acceleration of forgery detection in media. So here's the motivation. The line between distinguishing fake and real media is thinning. Due to the advent of technologies such as deepfake, Photoshop, and etc., it's getting easier and easier to fake media content. But this can have the effect of social political impacts in the form of swaying public opinion, discrediting people, as well as the threat of blackmailing people. Media forensics is the field of developing technologies for the automated assessment of the integrity of an image or video. And for acceleration, we aim to accelerate inference time without sacrificing the accuracy of these techniques. Here's an example of forgery. On the left, there's a woman tearing up the Constitution, and on the right, there's a German politician giving the middle finger during a speech. Here's some background on how fake content is generated. There's adding, replicating, or removing objects from a different image, known as splicing, or from the same image, known as a copy move. There's also extending the background to cover something, known as in-painting. On the right are examples of these techniques. These can be done with or without artificial intelligence. Autoencoders and generative adversarial networks can make stuff from scratch. An example would be face synthesis. Here's an example of deepfake, and there's a link that teaches you how to do this in 5 minutes.
Methodology. So there are several methods to authenticate images. The first one would be blind methods, where you take the image as face value and you search for discrepancies within the image to tell whether or not it's fake or not. There are sensor and model-based methods, which take the information of a specific camera or of a specific model of cameras to tell whether or not it's fake. And there's also machine learning, which uses convolution to tell whether or not an image is fake given a previous data set. Again, for blind methods, no prior information is required. You use the image that you have as face value, and you look for discrepancies. Some of those discrepancies might be CFA artifacts, which is color filter arrays, which is how an image is represented when it's taken by a camera and its RGB patterns. If there is a discrepancy on those patterns and in a patch in the picture, there is likely forged. There's also noise levels and noise patterns, where you look at the noise of an individual picture and see whether or not the noise is consistent or if there are some weird patches. There are some other methods like lens distortion, compression artifacts, and editing artifacts, but we didn't test those out in the paper.
Here's a summary of the methodologies that we tested. So there's 2 methods that we tested and optimized. The first method is using a blind method for image splicing detection, and the second method is optimizing a machine learning method, which also runs image splicing detection. Both methods use the Columbia Image Splicing Detection Evaluation dataset. Here's an example of the dataset. The authentic picture is on top and the spliced one is on the bottom.
To try to optimize it, we tested with MATLAB coder and with GPU coder, where we saw if compiled code was faster than the MATLAB code. And then we saw if code that was optimized to run in the GPU for parallel process was actually faster than just a regular CPU code. Here's an example of an unedited image, and then how the CFA artifact algorithm detects the image, where the brighter the color, the more likely it is to be fake. And then here is the same, where you have an unedited image, and using the noise level algorithm, where the brighter the image is, the more likely it is to be forged.
So method 2 is a method for optimization for machine learning. We implement the convolution in FPGA Verilog. We use Python's time.time to measure the original runtime without optimization. And then we use clock cycles and frequency to measure the FPGA code runtime. The CNN method is a process of taking the convolution of the desired image with a certain kernel, linearizes the output, and it gets the maximum weighted output. The algorithm we optimize does extra processing through local patches, where they analyze specific patches and analyze that section only with the context within that patch. Convolutional layers are the most computationally intensive and are commonly responsible for more than 90% of the CNN execution time. And this is why we try to optimize it.
So for convolution, you have a kernel, which is an array of pixels. You have the image, which is a 2D array of pixels. And you just multiply the kernel over the image over and over again with a certain step size to get the output. Here in the example, you see that you multiply a section of the image with the kernel to get an output just for one place. So what we decided to do was do convolution in the FPGA. And since convolutions are just summations and multiplications of arrays, the FPGA is nice since it can be general and it can be reused given a certain kernel size and given a certain image size and step size. Then we also decided to parallelize the process. So rather than doing the sliding window method that you saw earlier, we just split the image into its proper subsections where we will multiply them with the kernel all at the same time. That way it all runs in just a couple of clock cycles rather than all running at different times.
Here are the preliminary tests we did on blind and CNN. Here are the results of the accuracies. For CFA, the accuracy was 63%. And for noise, it was 38, which was significantly lower. And for the CNN, it was higher. We trained it for around 30 epochs, and these were the results we got. Here are the results from optimization. For the CFA, we got a really long time of 7 seconds after the GPU code was compiled into CUDA. This could be due to the code actually running in the CPU instead. However, we have it in CUDA, and it will be a lot faster when properly configured in the GPU setting. For the noise levels, we got a time of 0.4, which is still considerably higher than the compiled and regular MATLAB time. For the compiled time, it's lower than the MATLAB code, as well as it was half the time for noise levels.
For the CNN method, what we did to test is we were given a specific kernel, specific image, specific step size of 2. That way, we would expect the same output out of every method. Then we would be comparing apples to apples, making sure that all the times are consistent. So for the FPGA implementation, after we split the image up and we parallelized it, it actually only took 3 clock cycles for the whole algorithm to be done for one image and one kernel. For the results, we tested on an FPGA target, which is the RS2. For PyTorch, we ran the code 1,000 times to get a good sampling rate, and we figured out that each convolution took around 1.5 times 10 to the negative 5 seconds. And when we tested it with the FPGA, it ran at around 1 times 10 to the negative 7 seconds. And then when we parallelized the whole system, it actually ran at 4.5 times 10 to the negative 9 seconds, which is significantly faster than running it by PyTorch.
So here's a summary of the implementation. The blind method was successfully converted from MATLAB code to CUDA running on the GPU. The results, however, were much slower than what was expected. For the machine learning method, it was successfully demonstrated to be realized in an FPGA. We implemented a proof of concept of convolution in Verilog via model sim Quartus. However, acceleration in Vivado failed due to some reasons in the test bench. Other failed attempts include TensorRT. This was due to it being prioritizing edge devices. TVM was a little too complex, and there weren't too many NumPy operations to be optimized in Numba. The results were much faster than expected, around a 3,000 times increase.
These are the references that we used. Thank you very much for listening.